What's going on, guys? Let's look at this problem right here. Here the first question is asking, a germanium sample is doped with 3 times 10 to the power of 13 antimony atoms per centimeter cube. Using the requirements of space charge neutrality, calculate the E minus concentration, actually electron concentration, N0 at 300 Kelvin. So here they are saying space charge neutrality. This means the positive charge is equal, the total positive charge is equal to total negative charge, which can be written as this way. We can write Nd plus P is equal to Na plus N. And here they are saying this is an antimony atoms, right? Doped with antimony atoms. Antimony atom is a pentavalent or trivalent and pentavalent impurities. So this is going to be an N-type semiconductor, right? For an N-type semiconductors, we are going to have, most of them are going to be N. Actually, donors are electrons, right? So we are going to have electrons most of the time. So by charge neutrality principle, we can cancel this P and Na, right? Because we are going to have this Nd and N, because we are going to have the electron most of the time. So we can say Nd is equal to N, and we know therefore N is equal to Nd. That's given right here. That is 3 times 10 to the power of 13, right? So we don't have to plug any equation or anything. The answer is directly giving the value. Like the value is directly giving the answer, right? So that's 3 times 10 to the power of 13 per centimeter cube. So this is going to be the answer for the first question. Now let's look at the second question. Second question is asking, show that the minimum conductivity of a semiconductor sample occurs No is equal to Ni square root of mu P over mu N. And also they are asking to find out sigma minimum. Okay, so this is conductivity. Now let's go ahead and prove this one. This is kind of proof question. So to find this one, first we have to find we have to know the conductivity equation that's given by sigma is equal to NQ mu N plus PQ mu P. Okay, which also can be written as N0 Q mu N plus P0 Q mu P. Okay, so here they are asking to derive the equation in terms of N0. So we have to get rid of this P0. We know that according to mass action law, P0 is equal to Ni square divided by N0. So we can replace this P0 with Ni square divided by N0. So we are going to have sigma is equal to N0 Q mu N plus Ni square divided by N0 Q mu P. Okay. Now here we have to prove the minimum conductivity. So whenever we have to show minimum or maximum, we have to take the derivative. So here we have to take the derivative of this sigma with respect to N0. If we do that, the first N0 is going to become 1, and these are constants, so that's going to remain the same. So we are going to have Q mu N. And if we take the derivative of this one with respect to N0, since N0 is in the denominator, this is N0 power minus 1. So we will have, if we take the derivative, that's going to be minus N0 power minus 2. So we will have a minus here, and Ni square N0 power minus 2, that's going to be in the denominator, we are going to have N0 square, right? Then Q mu P, those are constants, so those are just going to remain the same. And then we have to equate this one to 0. Now here we have to derive the final equation in terms of N0. So also you can see this, if we bring this one to the other side, we are going to have something like this. Q mu N is equal to Ni square divided by N0 square Q mu P. Okay, so here Q and Q cancels each other. So this Q and this Q cancels each other. Finally we will get N0 square is equal to this one. So N0 square is equal to Ni square times mu P over mu N. And if we square root this both sides, we are going to have N0 is equal to Ni square root of mu P divided by mu N. So that's the first derivation. That's what we are having right here, right? So we got the same thing. So this is a proof question. The first part is proof, and the second part is asking us to find out the sigma minimum. Now to find the sigma minimum, what we have to do is we just have to plug this value instead of N0 all the places. here we have n naught, and after we derive this one, okay, we have to use this one because here we have p naught. We found out p naught is equal to ni square over n naught by mass exn law, and we derived this one n naught ni square over n naught. So we have to replace this n naught and this n naught to find out the sigma minimum. So sigma minimum is going to be what? We are going to have ni, instead of n naught I am placing this one, so instead of n naught right here we are going to have ni sigma, actually sigma, not sigma, square root of mu p over mu n times q mu n plus, here we have ni square over n naught, so ni square, instead of n naught I am placing this one, so ni square root of mu p over mu n, and then that one multiplied by q mu p, so this one multiplied by q mu p. Now let's cancel everything we can cancel. This ni and this square can be cancelled, and that's it for this one. And also if you look at this one, when we have something like outside, this mu n can be written as square root of mu n multiplied by square root of mu n, right? So we can calculate, like do this, like if you multiply 2 square root of mu n, you will get mu n. So if you think that way, you can cancel one of the mu n in the numerator, so we will end up with one of the mu n here, right? So if you simplify, I get rid of this one. Since we are done with the first part, let's try to simplify this one on top. Okay, let's get rid of this part. And I'm continuing this part on top. Okay, let's use a different color. Okay, so we'd have end up with this one. Here I can do one more thing. I can take the ni common. If I do that, we have a square root of mu p already there, and I told you, like when we have mu n outside, we can write it as square root of mu n times mu n. So one of the mu n cancel here, and we will have one of the mu n in the square root in the numerator, right? Plus again for this one, this square root of mu n will flip around, the denominator square root of mu n will flip around and go to the top. This mu p cancelled with this mu p. In the same way, when we have mu p, we can write it as square root of mu p times square root of mu p. So one of the mu p will cancel with the denominator mu p, so we will end up with square root of mu p times mu n. And also we have q remaining, so we have to write that one outside. And finally we will end up with, so this is ni, and then we are adding this one 2 times. So here we have this one 1, this is 1. So when you add these two together, we are going to have 2. So we are going to have final expression is going to be 2 sigma minimum is therefore 2 ni q square root of mu p times mu n. So this is going to be the final derivation. And that's how we do this kind of problems. I hope this helps. Thanks for watching.